Good evening, everyone. Today I am going to take class about the solution chapter class 12. This is the lecture 3. In the previous lecture, we have discussed about the Raoult's law, Henry's law, and the vapor pressure of liquid-liquid solution, and also discuss some MCQ question. But in this class, we will start from ideal solution and non-ideal solution. We will discuss about the ideal solution and non-ideal solution. So when I am talking about the ideal solution and non-ideal solution, that means there is lots of possibility to make the solution. Suppose we know that solutions mean there will be solid plus solvent equal to solution. Okay, but there is lots of possibility of solid and the solvent. When the solvent is liquid, it could be solid, it could be liquid, it could be liquid, it could be liquid, somehow it could be the solid. So there is a lots of possibilities there to make solution. Okay, but here when we are going to discuss about the ideal and non-ideal solution, basically we will discuss about the liquid solution. Liquid solution. So liquid solutions means they are solid also is liquid and solvent also is liquid, and they will make the liquid solution. So this liquid solution could be classified the two categories. One is the ideal solution, another is non-ideal solution. One is ideal solution, another is the non-ideal solution. So now how we will know which one is that, which one is the ideal solution and which one is the non-ideal solution? So there is the some properties and the some characteristics also is there to know that is the ideal solution, that is the non-ideal solution. So first we will discuss about ideal solution. So we know that the Raoult's law, we know that the Raoult's law, from the Raoult's law we know that the partial pressure is is proportional to their mole fraction, and from that partial pressure equal to Kh into x1, where the Kh is Henry's constant, but that if I change that is the P0 x1, then it is the Raoult's law. So this is the Henry's law and this is the Raoult's law. So for that Henry's law there is the Henry's constant, and for the Raoult's law it is the pure vapor pressure of the pure component. Okay, so for the ideal solution, which solution we will say that it is the ideal solution. The ideal solutions means it follows, it always follows the Raoult's law, follows the Raoult's law. So this law, the solution, suppose a solution it follows this Raoult's law, then we can say it is a ideal solution. Another properties is that, another characteristic also is there, the mixing of the two liquid. Here I am saying that the liquid solution, so that means the two liquids are the mixing to each other. So when these two liquid, suppose A and B, these two liquid, suppose A and B, the two liquids will be mixed to each other, then the mixing volume will be 0. The volume of the mixing will be the 0. That means the total volumes of the solutions, and so that means that total volume of solution equal to volume of component A plus volume of component B. Okay, so these two volumes, so this is the solute and this is the solvent. So the sum of the volume of the solute and sum of the volume of the solvent is equal to the total volume of the solution. Then we can say the mixing of the volume of the solution will be the 0, and also we can say it is an ideal solution. And the third condition is that delta mix A is equal to 0. It means that when we are going to when the two liquids are mixed to each other, then there will be no gain of heat and no release of heat. So that means when the two liquids are the mixing, no gaining of heat and no releasing of heat. That means it will be it will be it will be a adiabatic process. It will be adiabatic process. There will be no change of the heat. It will be not the exothermic process. It will be not the endothermic process. So when these three criteria will be there, we can say this liquid solution is a ideal solution. And also there is another criteria. Is that what will be the another criteria? Suppose uh, uh, here I have said that it is a liquid solution, so solute is a and another solvent is a B. So when in a liquid solution the solute is A and the solvent is B, so in the solution medium, so there is the three possibility of intermolecular attraction. Suppose one attraction will be there, AA. AA means between the two solute particle there will be a intermolecular attractive force. Okay, we can say it is a force. Okay, so there is also BB. So BB means this is the AA. That means between the two solute particle there will be a intermolecular attractive force, and BB means there is a two solvent molecules. So between these solvent molecules there will be intermolecular attractive force. Also another possibility, AB. AB means between the solute particle and the solvent particle. Between that there will be a intramolecular attractive force. So these are possible intermolecular attractive forces. So for that ideal solution, what will be that? For the ideal solution, this attractive force, and this attractive force will be the equal. So if the solution is the ideal, then the intermolecular attractive force between A and AA, this attractive force, and the BB, this attractive force, and the AB, this intermolecular attractive force will be equal. That means we can say also like that AA equal to BB. So this attractive force equal to will be like that. So there are the four criteria to know which one will be the ideal solution and which one will be the non-ideal solution. So for that ideal solution, it follows the Raoult's law that delta mixing volume will be the 0, delta mixing H will be the 0. So there is the no change of the volume, there is the no change of the enthalpy, and also there are the three possibility of intermolecular attractive force, A, PB, and AB, and these three intermolecular attractive force will be equal for that ideal solution. So these are the classification of actually liquid solution. Just remember that if it is the liquid solution, then we can say it could be the ideal solution and it could be the non-ideal solution. But for that ideal solution, it always follows the Raoult's law, and delta mixing volume equal to 0, delta mixing enthalpy is equal to 0, and there are the three possibility of intermolecular attractive force, AA, BB, and AB, and this attractive force will be the equal. So these are the criteria for that ideal solution. Now we will know about the non-ideal solution. So what will be the criteria for non-ideal solution? So for that ideal solution, we know that it follows the Raoult's law. So for the non-ideal solution, it does not follow the Raoult's law. Okay. So when a solution does not obey the Raoult's law over the entire range of the concentration, then we can say it is a non-ideal solution. So what will be that? When a solution does not follow the Raoult's law, so there will be the change of the vapor pressure. Okay. So how it will be that? We know that. So to know the point actually for the Raoult's law, so it does not follow the Raoult's law. So we know that the Raoult's law, for that Raoult's law, the graph is like that. Okay, that one is the P1 0, suppose that one is the P2 0, and that one is the x1 equal to 0 to the x1 equal to 1, and x2 equal to 0 to and x2 equal to 1, 1. And when we are going to so it will be the pressure, the partial pressure P2, it will be the partial pressure P1, and this is the total vapor pressure, of the solution. Okay, so this is the, so this line is, so this line is for the vapor pressure of the solution, and this is for the solute 1, and this is for the solvent, suppose. So this is for that the Raoult's law, when a solution obey the Raoult's law. Okay, but when a solution that does not follow the Raoult's law, then that will be not the curve. So that will be not the curve of the vapor pressure. So there will be the some difference. First one is that when the vapor pressure is lower, then the solution exhibit the negative deviation. When the vapor pressure is the higher, then the solution exhibit the positive deviation. What is that? Okay, so there will be the two deviation. One is the positive deviation, another is the negative deviation. So just I am writing here. So first we will know about the positive deviation. So there will be positive deviation of vapor pressure, positive deviation of the vapor pressure. So when there will be the positive deviation, that is the important thing. So we know that it is a liquid solution. So that means the solid will be also liquid and solvent also will be the liquid. So let us consider the solid component is A and solvent component is B. Okay, so we know that there is the three possibility of the intermolecular attractive force. So AA, BB and AB. So these are the three attractive force will be there in the liquid solution. But when AB interaction are the weaker than AA and the BB, that means AA interaction and the BB interaction is higher than AB interaction. So you just think about that. When AA interactions means solute particle interaction, BB interactions means solvent particle interaction. So when this type of the interaction is there, and also this attractive force is greater than solute solvent molecule attractive force AB, then 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 there will be the positive deviation. But how it will be the positive deviation? When the AA and the BB interaction is higher. So when the AA and the BB attractive interaction is higher than the A and the B attractive interaction, for that case A molecules and the B molecules will find and easier to the escape than the pure state. So that interaction is higher means, suppose for the AA solvent, AA solvent, AA, that is the vapor pressure for that A. For A component, the pure vapor pressure is, suppose P10, this is the vapor pressure line. But when the AA interaction is higher, that means this vapor pressure line will be like that. So there is a attractive force interaction between the AA. So vapor pressure will be the vapor pressure of the A component will be the higher, because the attractive force of the same molecules is the greater than A and the B. So that's why there will be the positive deviation. So for that positive deviation case, what will be the curve? So the curve will be like that. This one will be the x1 equal to 0, x1 equal to 1, x2 equal to 1, x2 equal to 0. So x1 is increasing here, x2 here increasing. This is the vapor pressure curve. So this is the P10 and this is the P20. So this one, the vapor pressure of A component. So this is the for ideal condition, and this is also the ideal condition, and this is also the ideal condition. So this is the vapor pressure of the solution, this is the vapor pressure of A component, and this is the vapor pressure of the B component. But when there will be the positive deviation, so AA interaction and the BB interaction is greater than the AB, so every component the vapor pressure will show the positive deviation. So it looks like that. So every component will show. So A component also show the positive deviation, B component also showing the positive deviation. So the total vapor pressure of the solvent, it also show the positive deviation. So that is the positive deviation curve, deviation vapor pressure curve for non-ideal solution when AA interaction or the BB interaction is greater than AB interaction. That means when the solute-solute interaction, solvent-solvent interaction is greater than the solute-solvent interaction. So there is example, suppose that for example we can say what it looks like that. So it is a mixture of ethanol plus acetone. So ethanol here is a solute and acetone is a solvent. So there is interaction of between these two ethanol is hydrogen bonding also is there. So this interaction, so this is also A, this is also A. So this interaction is greater than that interaction. So this is the A and the B interaction. So this interaction is higher than AB interaction. That's why it is showing the positive deviation. And then the Raoult-Slough curve, it will be like that. So so this will be the exact curve. Okay. So this the positive deviation curve will be the exact curve when positive deviation will be happened for that non-ideal solution. So what will be the negative deviation? What will be happened for the negative deviation? So for negative deviation, the opposite will be happened. What will be the opposite? That we have to know. We have know that it is a liquid. It is a liquid solution. So component A, this is the component B. So there is the two possibility. So there is AA interaction, BB interaction, and the AB intermolecular attractive force. So this attractive force is there. But when the negative deviation will be happened, that means AA interaction and BB interactions will be weaker than the AB interaction. What will be that? So you just like that actually. So we know that for that ideal solution curve, for that Raoult's law, from that Raoult's law, and for the ideal solution, they follows this curve actually. Okay, so this is the curve. There is the no negative deviation. There is the no positive deviation. All the interactive force, all the attractive force are the equal. But when the solute and the solvent attractive force is weaker than solute solvent attractive force. That means the vapor pressure of the solution. So this attractive force is the weaker. Solute attractive force and solvent attractive force is the weaker. So when that attractive force will be the weaker, that means the ideal vapor pressure of the A, that means the vapor pressure of the pure A and also the B will be decreased. So that vapor pressure and that vapor pressure will be show the negative deviation. So then it looks like that curves will be looks like that. This is for B component and this is for the A component. So this is for the A component and this is for the B component. So you just think about that when the vapor pressure of the pure A component is decreased and vapor pressure also of the pure B component also is decreased. So the total volume, so the total vapor pressure of the solution, that also will be the decrease. So it will be like that. So this is the total, that will be the total vapor pressure of solution. Okay, so this vapor pressure also is decreased due to the weaker uh, intramolecular attractive force. AA and the BB is the weaker than the A and the B. That's why it is showing negative deviation. It is showing the negative deviation. So now if I talk about one example, that will be the very interesting example, the mixture of phenol and aniline. So for the negative deviation, I have said that the AA interaction, BB interaction will be the weaker, but the AB interaction will be the higher. So that means between the phenol and the aniline, this attractive force will be higher. How it will be like that? So this is the interactions between the lone pair and this protic part. This is the proton. So this interaction between this proton and the lone pair, so this attractive force is greater than another force. So this is the AB interaction, but this interaction is very weaker. This is the AA interaction and this is the BB interaction. Because why I am saying that these two interactions are the very weaker, because if you say, so there is the lone pair also is there is the lone pair also is there, but if you compare the protic, if we compare this proton and this proton is the more acidic than that proton. So OE's proton is the more acidic. So OE's proton is the more acidic than the amine proton. That's why there will be a greater attractive force between the proton and the lone pair for that A and the B interaction. So BB interaction is the weaker. But in that case also, in that case, if you say, so this proton is the same, but there is the lone pair, there also is the lone pair. But this attractive attraction is the less, is the weaker than that. Why? Because we know that oxygen is more electronegativity, more electronegative atom than nitrogen. That's why this lone pair is more free than that. So this lone pair is the bounded. So this lone pair is not too much free compared to that. That's why this AB attractive force is more higher than AA and the BB attractive force. That's why this vapor pressure is the negative deviation. So That's why this type of the deviation is called the negative deviation. So we know that the non-ideal solution. So for the non-ideal solution, there will be three criteria basically the two criteria. The solutions does not the follow the Raoult's law. When a solution that does not the follow the Raoult's law, that means there will be loss of the vapor pressure and also gain of the vapor pressure. When the vapor pressure will be the increase, that means it is a positive deviation. But when the vapor pressure will be the decrease, so it is the negative deviation. Okay, so here we have the learned some concept about the ideal solution and the non-ideal solution. So there is the some criteria to know the ideal solution. There is the some basic criteria for the non-ideal solution, and for that non-ideal solution there are the two things. One is the positive deviation and that is the negative deviation. Now another interesting point, we know some liquid, when the some liquid are the mixed to each other, suppose the two liquid are the mixed, okay, then there is a possibility of the same composition in the liquid phase and the vapor phase, and at a boil at a constant temperature, and then it is a azeotropic mixture. So what is that? So there is chance to make a azeotropic mixture from a liquid solution. What is the azeotropic mixture? Azeotropic mixture means it also for liquid solution. Okay, so for that liquid solution, when the composition, so this is a liquid solution, so it is in liquid phase. But if we boil at a fixed temperature, it can show the vapor phase. So there is the two possibility. Another also is there the solid phase, but I am not going to the solid phase because there will be lots of loss of the heat. Just I am talking about here the liquid phase and the vapor phase. When the composition of that solution in liquid phase and the vapor phase at a fixed boiling temperature, then we can say, then it is called azeotropic mixture. So for that azeotropic mixture, the compositions will be the same in vapor phase and the liquid phase. So when the vapor phase, so there are the two types of the azeotropes. One is the minimum boiling azeotropes, another is the maximum boiling azeotropes. What is that? That also we will discuss here. Minimum boiling azeotropes, so there is possibility here. I already said that at a fixed boiling temperature, whence the liquid phase, this is the liquid phase and this is the vapor phase. So this liquid phase and the vapor phase, the compositions will be the same. Then we can say it is a azeotropes. So there we needs a temperature. So depends on the temperature, we can say one is the minimum boiling azeotropes, minimum boiling azeotropes, another is maximum boiling azeotropes. So there is two possibility. One is the minimum boiling azeotropes and the maximum boiling azeotropes. So what is the meaning of that line? Because when, so minimum boiling azeotropes means at a minimum temperature, suppose suppose this liquid solution is just boiled at 30 degrees Celsius temperature, it just boiled, it just vaporized. So in this condition, in that temperature, in that minimum 30 degrees Celsius temperature, just boiled, so in that temperature, the composition of the vapor phase and the composition of the liquid phase will be the same. So that is the minimum boiling azeotropes. But what is the maximum boiling azeotropes? Suppose suppose that liquid solution is starting to boil the at just started at the 30 degrees Celsius temperature, but at that 30 degrees Celsius temperature whatever vapor phase is formed, but in that case and the compositions of the vapor phase and the liquid phase is not same. Suppose when we are increasing the temperature 30 to 35 and 40 degrees Celsius temperature, suppose we have seen that at the 40 degrees Celsius temperature it's the composition of the vapor phase and the liquid phase is the same. So 30 degrees Celsius temperature it started to boil, but at that 30 degrees Celsius temperature if the vapor phase and the liquid phase the composition is the same, then we will go to the minimum boiling azeotrophs. But suppose the temperature is increasing from the 30 to 40 degrees Celsius temperature, in that temperature, in that maximum temperature, the vapor phase, the composition of the vapor phase and the liquid phase is the same, then it is a maximum boiling azeotrophs. So the solution when so if we correlate with the non-ideal solutions with that azeotrophs, so when a non-ideal solution show the positive deviation, okay, when the non-ideal solution show the positive deviation, then it will show the minimum boiling azeotroph. So it will be the minimum boiling azeotroph. So there is a point if I write here, when a solution, when a non-ideal solution showing the positive deviation, then it is a minimum boiling azeotrope. This is a minimum boiling azeotrope at a specific composition, as a specific composition. So if we say some example, if we say the for example ethanol and the water mixture, here the 95% will be the ethanol and 5% will be the other. So another point also is there, when a non-ideal solution show the negative deviation, then it is actually maximum boiling azeotrope. For example, composition the mixture of nitric acid and the water. So in this composition the 68% will be nitric acid in composition and 32% will be the water. So azeotropes means, so there will be compositions will be the same in the vapor phase and the liquid phase. That is the main point. And also, so when the compositions will be like that, so it will be the non-ideal solution. So for the non-ideal solution, there is the positive deviation, there is the negative deviation, and there is the one point is another term is the azeotropes. So these azeotropes will be maximum boiling azeotrope, it will be the minimum boiling azeotropes. So here I will stop the class. So in this class basically we have learned about the ideal solution and the non-ideal solution for a liquid solution. So in the next class we will discuss about the colligative properties and the determination of the molar mass. So it is a very important thing how we will calculate the molar mass. Also I will discuss about the molarity, what is the molarity, what is the normality and the molality. So we will discuss about the some terms of the mole actually, and also about the colligative properties. So here I will stop the class and I will discuss about some MCQ question that already given in the previous class. So just I will say the answer and also I will say the tricks how you can easily calculate easily the solve this type of the MCQ question. So in the previous class already I have given this 10 MCQ question. So these MCQ question are basically numerical type. So there is the no mathematical um, MCQ. So first MCQ is the volume occupied by a single gas in a mixer at the same temperature and the pressure is referred to as a single gas volume. Okay, so what is that? When a volume occupied by a single gas in a mixer, suppose it is a mixer, so suppose it is a liquid a solution. Okay, but in this liquid solution, some volume of the gas is present is there. So bubbles will be the created inside the solution. So in a fixed temperature, in a fixed pressure, so is referred to as the single gas volume. So the what will be the what will be the volume of that case? So whence a liquid solution, in the presence of the liquid solution, there will be some single gas will be there at a fixed temperature and the fixed pressure. So then we cannot say the exact volume. We cannot say the exact volume of that liquid A. We cannot say the exact volume of the liquid B and the gas. So in that case, there are the three component, liquid and the gas also is there. So three component also is there. So we will have to use the partial term. So there will be the partial volume will be the exact answer. Question number 2, the pressure that a single component, so there is a single component in a gaseous mixer would extract, and if it is a excited alone in the same volume as the mixer and at the same temperature as the mixer is referred to as. So this is also the same question, that also about the pressure. Why I am talking about the pressure? Because the pressure here is the volume. So what will be the volume? So it will be the partial volume. What will be the pressure? It will be the partial pressure. Because when we are going to the mixing composition, so there is the lots of the component is there, then we will say it is not a absolute pressure. It will be not a total pressure. It will be a partial pressure. It will be a partial volume. So this type of the MCQ questions will be also important for the 1 mark. Now for that MCQ number 3, that's the obey the Raoult's law in all the stages of the concentration. Already I have said that the ideal solutions always the obey the Raoult's law in all the stages of the concentration. Whatever in all the range of the solution, that this is the liquid solution. So over the all the range of the solution, the particles, the liquids, the solutions, they will obey the Raoult's law. The question number 4, whence the two perfect solutions with the volumes of V each are the combined. So what is the volume of the solution as a result? So this is a interesting question. So what will be the volume when the perfect solution? So perfect solutions means it will be the ideal solution. So the options will be the A, because for the perfect solutions, the when it is the combined, also the solutions, the volume of the solution also the will be the V. Sorry, it will be the 2B, because it will be the 2B answer, because already I have said that in that class that A volume and the B volume will be the sum of the sum. Okay, so V plus V will be the 2B. So option B will be the correct answer. Now the heat of the solution or the mixing has a negative side. So that is the important thing. What will be that when it will be the negative, when it will be the negative. So delta mixing V will be the negative also, delta mixing H also will be the negative. So it means negative, that means it is a exothermic process. Exothermic process, this is the important question, and that is the negative means dissociation is happening. Dissociation is happening. That means the AB is divided A plus B, like that. So heat of the dissolution. Okay, so that will be the answer. Now, a solution made up of numerous components in which the each component's property is the weighted sum of its separated properties. So what will be the answer for that? It is a ideal solution because the sum of its the separate properties. Already I have said that AB volumes will be the sum of the component. What is the total volume will be the sum of the volume of the each component. So that is the thing. Now, what is the example of that is the common for in the nitrogen gas? So it is a out of not the out of, if you think that is will be the very interesting thing. So what is the example of camphor in the nitrogen gas? So you see, so this is a composition of a solution. This is a composition of a solution where nitrogen gas, so it is a gaseous medium, so it is a solvent. Now camphor is also a, so it is a solid. Now we have to know what is the state of the camphor. So the state of the camphor is solid. So solid in gas. So 7 is the answer. Solid in gas, gas is there, nitrogen gas is there, so it is a huge amount. And also we have to know, already we know that always the volume of the solvent is greater than the solid. Okay, so here the nitrogen gas, the volume of the gas is the high, so nitrogen gas act as a solvent and the camphor act as a solute, and the camphor is a solid, so answer will be the solid in gas solution. So what happens when a solid crystal is added to a supersaturated solution? So it is a supersaturated solution. So in this supersaturated solution also I am adding a some crystal, some solid I am adding. So what will be that? So it is a, suppose it is a saturated solution, then there will be no problem. So for that if it is a saturated solution, so there will be the no problem. When it is a saturated solution, in this saturated solution if I add the solid, then the concentrations of the solution also increasing, so then it will show the dissolution process. But when it is a supersaturated solution, that means there will be no chance of the solubility of the solute. Okay, if we add that some solid particle in that saturated solution, so there is the 100% chance of the precipitation. Okay, so there is the 100% chance of the precipitation. So option D is the correct answer. So which of the following option is not a right actually? So this is a totally I think it is a totally out of content that I didn't till now I didn't teach about that. So the options will be that D, this is a acidic drinks. Okay, so option for that question the number 10, what makes a solution? That is a very easy. When the solute and the solvent is there, so it will make a solution. Not solute, not solvent, none of above. So when the solute and the solvent is there, it is a solution. That already I have taught, already I taught in the first class also is there. Okay, when solid is there, solvent is there, it will make a solution. And in the solution case, the volume of the solvent will be always the greater than the volume of the solute. Okay, so here I will stop the class. And already I have teach about the 80% of the solution chapter. So others the 20% about the colligative properties, and also some concept of the molar mass and the molarity, normality also I will teach in the next class. So if you have any problem, you can ask the question in the next class. Okay, thank you.